Hello, this is Unit 2 of AP Physics, and in Unit 2 we're going to deal with dynamics. For our agenda of the lesson, we're going to go ahead and talk about systems, and we're also going to go ahead and talk about Newton's third law. More detail, our objective, students will be able to define what is a system and learn about gravitational fields. We're also going to discuss the relationship between force, mass, and acceleration. And finally, we're going to go ahead and use Newton's third law to solve problems. Alright, so let's go ahead and start with what is a system. Here are two pictures right here giving us two examples of a system. For a little boy pushing the cart, that would be a system. That's what we're studying. How much force is this little boy applying to that cart? And what is the acceleration of the cart? So that's an example of a system. Here we have a picture of the moon and planet Earth. They're not touching each other, but nevertheless there is a force between them, gravitational force. So that'll be another system that we could study as well. So here it says a system is an object, for example the cart, or collection of objects like the moon and the Earth, interacting via forces or other processes that are internal to the system. Alright, so let's dig a little deeper. The internal structure of a system determines many of its properties, such as the charge. If we really look at, for example, a proton versus a neutron, it is the parts that give some different properties. For example, a neutron is neutral and a proton is positive. So protons and neutrons are made of fundamental particles called the quarks. Electrons are a fundamental particle. For a proton, it's got three quarks. Same thing for a neutron. For a proton, though, we'll have two quarks that are labeled as up and one that is down. Whereas the other side, neutrons will have only one quark that is up and two that are down. So that gives them the slight difference on the behavior. Now, let's move along to a gravitational field. Any object that has mass will give you a gravitational field. So it says an object with mass will cause gravitational field. The gravitational field will cause a gravitational force, which is mass times gravity. So that's how you calculate the force. It is the mass of the object multiplied times the gravity in the direction towards the object that is creating the gravitational field. Alright, and here's a neat little picture of, let's say, a planet, and it bends space-time, and that's going to go ahead and create gravitational field. Okay, on Earth, the gravitational force is called weight. So when we ask you how much do you weigh, most people give the answer in pounds or kilograms. Now, the answer should be given in newtons. Okay, so how we're going to go ahead and calculate that? It says the gravitational field is measured by dividing the gravitational force exerted by the field on the object by the mass of the object. So here we go. Our weight is the gravitational force. You divide it by the mass, and that will give you the gravitational force. On Earth, the gravitational force is numerically equal to the free fall acceleration of an object, which is 9.8 meters per second squared, though most of the time in our calculations for AP Physics we end up using just 10.0 just to make it a little bit easier and a little bit quicker. Alright, let's go ahead and move along. We'll go back to this formula a little bit later on. Alright, in this problem we're going to go ahead and solve for the relationship between force, mass, and acceleration. So we have an example. It says a father pushes his kids on a sleigh with a constant force of 50 newtons. Each of his three children have a mass of 20 kilograms, 30 kilograms, and 50 kilograms. And they ask you to go ahead and calculate the acceleration for each child. Alright, so we're going to go ahead and do that. And what is the formula we're going to go ahead and use? It's going to be this one. Force equals mass times acceleration. So we want to know the acceleration. And so because we want to know that, we're going to isolate the A. So we've got to get rid of the m. So we're going to divide by m, by the mass. And there is acceleration. It's just force divided by the mass. For our first child, they have a constant force that is being exerted by the father as he pulls. And the mass is going to be 20 kilograms. Alright, so then they ask you what will be the acceleration for this. Let me go ahead and get my calculator. Alright, and all we got to do is divide the mass, the formula divided by the mass. So the force divided by the mass is 50 newtons divided by 20 kilograms. And that's going to go ahead and give us the acceleration. Okay, so it's going to be 50 divided by 20 gives us 2.5 meters per second squared. Okay, next, for our second child, we're going to go ahead and do the same procedure. It is 50 newtons, but this child is heavier. So what happens to the acceleration? If the father is still providing the same amount of force, it's going to be 50 divided by 30. We're going to round it up to 1.67 meters per second squared. So it went down. For the third child, who's the heaviest at 50 kilograms, father's still pulling with the same constant force of 50 newtons, and the child weighs 50 kilograms, so 50 divided by 50 is going to give us an acceleration of just 1.0 meters per second squared. Okay, so looking at this, if I were to ask you, what is the relationship between mass of an object and the acceleration of that object? And you say, well, as the mass increases, the acceleration decreases. That makes they are inverses of each other. When the mass goes up, the acceleration goes down. Let's move along to our next problem. In this one, they want graph the mass versus acceleration. Draw the mass on the x-axis and the acceleration on the y-axis, and again they ask you what is the relationship. Alright, so the relationship, one more time, we know what it is. As the mass increases, the acceleration is going to decrease, so that's the answer to that question. But let's go ahead and graph it. And here they ask, mass will be on the x-axis, so let's go ahead and put it. Let's start 0, 10, 20, 30, 40, and 50. So that's our mass. And they want the acceleration on the y-axis. So it goes from 1 all the way to 2.5. So let's just go 0, 1, 2, 3. Alright, so that's a rough graph right here. First one at 20 kilograms and 2.5. So we go 20 kilograms and 2.5 will be somewhere around here. Let's see, 30 kilograms and 1.67. So there's 30 and 1.67 somewhere around here. And last one, 50 kilograms and 1.0. Will be right around here. So there we have it. So as the mass increases, the acceleration decreases, so they are inversely proportional to each other. Alright, let's go ahead and move along. For this next example, they're going to go ahead and say the father wishes to pull all the kids with the same constant acceleration. Yeah, so now you want them all to get the same acceleration. So what would you have to do? So they ask, calculate what force you would need to get that acceleration. So let's go ahead and take a look at this formula again, and this time we will need just to multiply the mass times the acceleration to figure out how much force does the father need to apply to get the same acceleration. Alright, they want the acceleration to be 2.5 for each of the children. Alright, so we're going to have the acceleration here, mass, and now we want, what is the force? Alright, again, to calculate the force, it's just mass times acceleration, so it's going to be 20 times 2.5, that's going to go ahead and give us 50 newtons. But for the heavier child, it's going to be 30 times 2.5, he's going to require more energy, 75 newtons. And lastly, for the heaviest child, 50 times 2.5 is going to give us 125 newtons. So if you want to go ahead and keep the acceleration constant, then you're going to have to apply more force because you have a heavier child. Alright, so that takes care of this section. The next one they ask us, can you please go ahead and draw a graph and describe what is the relationship between mass and force. So the larger the mass, the larger the force you're going to need. See, as they both increase. So they are directly proportional. Okay, so let's go ahead and draw a graph. And for the graph on the x-axis, we're going to put the mass. And put 0, 10, 20, 30, 40, and 50. So it's a rough graph right there. And they're going to want the force on the y-axis. Okay, so we're gonna go 0, so we'll go with 50, 100, 150, and that is our force in newtons. That's our mass in kilograms. Alright, so for our first one, 20 kilograms, you needed 50 newtons. So that'll be right here. At 30 kilograms, you needed 75 newtons, so that'll be somewhere around here. And finally, at 50 kilograms, we needed 125. So it'll be somewhere around here. And you can see that we get a positive slope. That means that directly proportional. As the mass goes up, the force also goes up. So that is the relationship between force and mass. Alright, let's go ahead and move along. Next, we're going to go ahead and talk about Newton's third law. Newton's third law states the following. It says Newton's third law of motion states that if an object 1 and object 2 interact, the force of object 1 on 2 exerted by object 1 on object 2 is equal in magnitude but opposite in direction to force F21, which is the force of 2 on 1 exerted by object 2 on 1. So here's our formula, and so essentially we're saying they are equal to each other except that one of them is opposite in direction. So if I apply a force this way, I'm going to get another force in the opposite direction with the equal magnitude. Alright, in the case of our picture right here, we have a hammer striking a nail. The hammer is providing a lot of force as it hits the head of the nail. How much force does the hammer receive in return? The answer is the same magnitude in the opposite direction. So that's Newton's third law. Alright, so we're going to go ahead and take care of our first example. In this one, they ask the following question. You have a man. This man has a mass of 75 kilograms and a woman whose mass is 55 kilograms. They're standing facing each other on an ice rink, both wearing ice skates. The woman pushes the man with a horizontal force of 85 newtons in the positive x direction. Assume that the ice is frictionless. What is the mass acceleration? That's part A. We're going to need to solve for the acceleration. Part B, what is the reaction force acting on the woman? And part C, calculate the woman's acceleration and name another force acting on the man and its pair. Alright, so let's go ahead and get to work on all of that. First, we need to write down all the information that we know. For the man, we know it's his mass. His mass is 75 kilograms. And for the woman, she weighs 55 kilograms. That is her mass. Alright, so we got that much. Now, they're facing each other. She pushes off of him, but the force that she is putting on him as she pushes is the same that he's putting back on her, even though he's not pushing. Alright, so she's pushing in the horizontal positive. So we're going to do a quick diagram. So there she is. And they're wearing skates. And she pushes on the man who's also wearing skates. And the reason why they put him on an ice ring is so that way the friction is zero. They don't want any friction in this problem. So she's pushing. So the positive direction is to the right. So keep that in mind. Alright, so again, A, what is the acceleration of the man? Alright, so we're going to use for part A this formula right here. Force equals mass times acceleration. Now, she pushed in the positive direction. He is accelerating towards the right, so his acceleration should be positive. Okay, so the force that was applied on him was 85 newtons, and that, the mass of the man is 75 kilograms. So your acceleration is what we're looking for. So we're going to divide by m on both sides to isolate the acceleration. So we're going to divide by 75 kilograms. And the acceleration of the man becomes 85 divided by 75, 1.13 meters per second squared. So that's the answer for part A. His acceleration towards the right, because she pushed him towards the right, is 1.13 meters per second squared in the positive direction. Part B. What is the reaction force on the woman? She put 85 newtons of force towards the right, which is positive. So the answer for B is how much is she going to receive? According to Newton's third law, the same magnitude, 85 newtons, but opposite in direction. So the force on the woman is going to be negative 85 newtons. So that'll be the answer for part B. Alright, because it's the same magnitude, 85 newtons, but in the opposite direction. Next, they want to calculate the woman's acceleration. How fast is she going? For this one, I'm going to make a prediction. Since she's got less mass, therefore she'll have more acceleration. So the man has an acceleration of 1.13. I expect her to have a larger acceleration because she's got less mass. Okay, so I'm going to put force for the woman. It is her mass times the acceleration. I want the acceleration, so we're going to divide by the mass. Alright, so it's going to be F over M. Remember that it's in the opposite direction, so that is 85 newtons over her mass. Her mass is 55 kilograms. And that's going to go ahead and give us her acceleration. So it's going to be 85 newtons divided by 55 kilograms. It's going to give us 1.54 meters per second squared in the negative direction because she pushed off, but she's going to go the opposite direction because the force is acting on her on the opposite direction. So there you go, it is negative 1.54 newtons. That is the answer for part C. In part D, they ask you, name another force acting on the man and its pair. Alright, so if I do a free body diagram, I'm going to squeeze it in here. There is obviously a force P for push, but there are more forces acting on the man. For example, there's a force due to gravity, and its opposite pair, the floor, is putting force on the man. That's why he's not accelerating downwards. So what do you call that force? It's called force normal, or normal force, either way. So that would be one force, and its pair is the normal force. So that's the answer for part D. Alright, let's go ahead and move on to the next problem. On this one, they ask you guys, a spacewalking astronaut of total mass of 148 kilograms exerts a force of 265 newtons on a free-floating satellite of mass 635 kilograms, pushing it in the positive x direction. What is the reaction force exerted by the satellite on the astronaut? B, calculate the acceleration of the astronaut. And C, calculate the acceleration of the satellite. So very similar problem to the one we did. Again, they want to get rid of friction, which is why we're in outer space, so we don't have to worry about friction. Alright, quick picture on this one. So we have our astronaut, he's in outer space, he's wearing his suit, and he pushes on a satellite. So there he is, and here's our satellite. There we go. He's going to push it on the positive direction. They give us some information on it. The astronaut, his mass, 148 kilograms. He pushes with a force in the positive direction of 265 newtons. So we're going to say positive towards the right on a free-floating satellite whose mass is 635 kilograms. Alright, pushing it on towards the positive x direction. So the force is applied this way, the satellite goes in the same direction. Letter A, what is the reaction force exerted by the satellite on the astronaut? Alright, so if this astronaut is applying 265 newtons of force in the positive direction, so the answer for A, what force is there for the satellite putting on the man, on the astronaut? The answer would be negative 265 newtons. So it's same in magnitude, 265, but opposite in direction. Alright, next, part B, calculate the acceleration of the astronaut. Alright, so for the astronaut, he's receiving this much force. And what will be its acceleration? Alright, so we're going to use this formula, force equals mass times acceleration. I'm going to divide again by the mass. Giving us force over mass is our acceleration. So acceleration is going to be force, negative 265 newtons. And the mass of the astronaut, it is 148 kilograms. So we have 265 divided by 148. 1.79 meters per second squared will be the acceleration, and they'll be in the negative direction. Let's squeeze that in here. There we go, in the negative direction, because he is accelerating that way, which is the negative direction. That is part B. In part C, they ask you guys, can you calculate the acceleration of the satellite? We're going to use the same formula, but this time we're going to put the force acting on the satellite, which is positive 265 newtons, and the mass of the satellite, who is much heavier than an astronaut, so therefore we should expect to get a smaller acceleration. So 265 divided by 635 kilograms. This is going to give us an acceleration of 0.417 meters per second squared. Much smaller acceleration, positive because the satellite's accelerating towards the right. Okay, so that goes ahead and takes care of problem number 2. Alright, now let's go ahead and take a look at problem number 3. In problem number 3, it says a person pushes a crate across a rough surface. Draw a free body diagram labeling all the forces when A, the crate moves at a constant velocity, and B, when the crate moves with a constant acceleration. So let's go ahead and start. I'm going to put it by free body diagram, which is just a dot. Alright, and the forces acting on it. Well, one of the forces is a man pushing on this box. So I'm going to put it in the direction that they're pushing, starting from the object going out, the arrow. And the length of the arrow represents the magnitude. And so I'm going to label it FP for force push. Working against the man is friction, because we have a very rough surface. So I'm going to put the same length. I put it F for force friction. And it's working against them, so I'm going to put, starting from the object, an arrow going out with the same length, so therefore they have the equal magnitude but opposite in direction. So they're going at a constant velocity, so that's why these two match each other. There's one more pair of forces acting on it, and that would be force of gravity and force normal. So if gravity comes from the planet pulling down on this crate, normal is from the floor pushing up. It's a contact force, so it's opposite in direction and equal in magnitude, so they're the same length for both of these. So that will be the answer for A. For part B, they ask you guys, now the crate has an acceleration. So when you have an acceleration, you have all the forces are not the same. One force got to be bigger than the other, so therefore there is a net force. Alright, so for part B, it's our free body diagram of our crate. Same force of gravity, same force normal. Force friction, we're going to keep it the same. But now it's accelerating. The man must be putting more force on this crate. So I'm going to put a longer arrow than that one. So it'll be force push. And notice how they're not the same length. And that's what's creating the acceleration. So you have a net force from the force push. So that's what creates acceleration. That takes care of problem number 3. Up next is going to be our last problem for this lesson. It's going to be problem number 4. In this one, a person pushes a crate across a rough surface. Again, now notice though that they're using a rope. They're actually pulling on it. So say A, draw a free body diagram labeling all the forces when the crate has a constant velocity including the components. Okay, and part B, draw a free body diagram labeling all the forces of the crate as constant velocity. Again, both of them have constant velocity, but do not include the components. Okay, so let's do part A. In part A, I'm going to put my free body diagram here. So there's my crate. The man is pulling with a force at 30 degrees, so just a quick dotted line right there. Roughly 30 degrees, and this is my force pull. In this case, alright, friction's still there, but I'm going to break it down into its components. This one, that's diagonal. All the other ones go straight up and down and side to side, but this one is diagonal force. Now it's important. So I put it as a dotted arrows. So those are the components there and there. What we call it, this guy's called force pull. Let me move it over here, force pull. And then I'm going to call this one force pull on the x-axis. And the angle is 30 degrees. And this I'm going to call it force pull on the y-axis. Alright, sweet. Next, I want to go ahead and put the force of gravity up next. I'm going to go ahead and go pretty low with that one. So it's force of gravity. Next, force friction. How much friction are you going to get? It's going to be the same as the force pull on the x-axis. So this length, I'm going to match it over here. Force friction matches the force pull on the x-axis. It's just opposite in direction. So they are the same length. Now, how much will be my normal force? Most students will tell me, well, it's going to be the same, as these two for force normal. And the answer is no, it's not actually that long. So how long is it? You got to take away some of the force from the pull on the y-axis because it is pulling slightly up on the rope. So therefore you see this length right here. I'm going to take it away from this arrow. And there we go. Now that's our force normal. It is less because this does have an upward pull. It is at a 30-degree angle, so it's a slightly upward pull, so that decreases the force normal. So in this case, the force of gravity and the force normal do not match. If you wanted to match, it would be force gravity, it would be force normal plus force pull on the y-axis. Then those two, add them together, that'll match the magnitude of the force gravity. The force friction will match the magnitude of the force pull on the y-axis. Alright guys, that is part A. In part B, they go ahead and they ask you, can you draw the free body diagram labeling all the forces acting on the crate at a constant velocity, but do not include the components? And there you go. That will be part B. All the forces, no components? There you have it. Alright, that goes ahead and takes us to the end of our lesson. Thank you for watching.